So gas evolution reactions, we talked about precipitation reactions, a solid forming when you mix two solutions. We talked about acid-base neutralization reactions, which are an acid and base neutralizing each other. And here, as the name suggests, we have a gas being formed or evolved. So you mix two aqueous solutions and a gaseous product is formed. Usually we see that as bubbles forming. Some reactions will form the gas directly from the ion exchange. So these we're also predicting the products in the same way of looking at the ions that came to the party and swapping partners and seeing if there's any chemistry, right? So if we do the ion exchange for potassium sulfide and sulfuric acid, we end up with potassium sulfate and dihydrogen sulfide. This is actually a gas. It looks like an acid, and if dissolved in water, it would function as an acid. But in fact, most of it bubbles out. So, and it smells really, really bad. Most sulfur compounds do not smell good. A lot of the odors from sewage have sulfur in them. So this one forms a gas directly. Other reactions form a gas because one of the products decomposes. It's unstable. And so this is what happens when you mix baking soda, sodium hydrogen carbonate, with an acid. One of the products is carbonic acid. Carbonic acid is unstable. And so it decomposes fairly quickly into water and carbon dioxide. And the carbon dioxide, of course, is a gas and bubbles out. Here we have an illustration. So mixing a sodium hydrogen carbonate solution with a hydrochloric acid solution. We've got hydrogen carbonate ions and sodium ions. We've got chloride ions and hydronium ions. So this is the hydrogen ion from the HCl. And the hydrogen carbonate ion will pick up that extra hydrogen ion and form carbonic acid, but the carbonic acid falls apart into water, which just disappears into the rest of the water, and CO2, which forms bubbles. So this is exactly what happens in those like kindergarten volcanoes, right? Where you mix baking soda and vinegar, and really fun, right? You can try that at home. Yes?
So like combined, because it's a soluble, like from that list of like solubles, it automatically starts to fall apart even though it has.
So this is going to be part of a new list. Yeah. Part of a new list. We can predict that the carbonic acid forms by swapping partners. And when we swap the partners, we'd get the hydrogen ion. We'd see H plus with the HCO3 minus. And we'd say, oh, well, let's put those together and we get this. And today we're learning that when we see that as one of the products, we recognize that that is going to form a gas. So these are the gas-forming products that we care about in Chem 1A. Of course, there are others that happen. So this is the one we talked about first. If you get H2S as one of your products when you swap partners, we need to just remember that that's a gas. So here where H2S shows up, we put G for its state symbol, and we just learn to do that. If we mix carbonates and bicarbonates with acids, we get the intermediate product carbonic acid, and this decomposes and forms CO2 in water. If from sulfates and bisulfates or hydrogen sulfates, we can get sulfurous acid, that decomposes into water and sulfur dioxide. Again, doesn't smell good. Ammonium can yield ammonium hydroxide, which is also unstable, and decomposes to form ammonia. So what we need to remember here is H2S and these three. The H2S just makes a gas, it's done. These other three decompose. And so this is what you're going to see as a product when you swap the partners. And then this is what happens to them Once you see the pattern here, it's not too hard to remember. So the H2CO3 is going to come apart. It's like a little Lego structure that doesn't stick together very well. It comes apart into two pieces. And one of the pieces is water. This is occurring at room temperature, so the water's a liquid. And then if I have a hard time remembering what the other product is, I can look at my formula here and just remove 2 hydrogens and an oxygen. So there's the 2 hydrogens, and I remove one of the oxygens, and what I have left is CO2. So that's the other product. And CO2 is a gas. We can apply the same process to the other 2 here, H2SO3. We swap partners, predicting products, and we see this, H2SO3, and we should say, oh, that's one of those unstable ones. So it also falls apart into a water molecule and something else. And again, we can predict the something else by taking the 2 hydrogens out and one of the oxygens to make that water molecule. And what we've got left is SO2. And like CO2, that's a gas. Ammonium hydroxide. Very different looking formula, but it does the same thing. It falls apart into water and something else. So again, I can look at the formula for ammonium hydroxide and say, well, I need to remove 2 hydrogens and an oxygen. So there's my oxygen. I'll knock this hydrogen off, and then I'll get rid of one of those, so instead of 4, I have 3. And what's left is ammonia, which is a gas at room temperature.
Which slide set are you on? I was just trying to pull it up.
Chapter 5.
Chapter 5?
Mhm.
Okay, not the chapter 5 continued?
So these guys, we just need to remember this is what they do. Now, this is not a big deal, okay? Stoichiometry, big deal. Calculating molar masses, big deal. Stuff like that. This, not a big deal, okay? So if you're struggling with the rest of the stuff, I give you permission to ignore the gas evolution reactions. It'll probably cost you 1 problem on the exam. No big deal. Here's an example. Write a molecular equation for the gas evolution reaction, and they're telling us gas evolution, so we should be on the alert. That occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Look at a little nomenclature practice here. So hydrobromic acid, that prefix hydro tells me there's no oxygen in this acid. It's hydrogen and bromine. So that's HBr and aqueous. It's hydrogen ion and bromide ion is what it forms when it ionizes in solution. And then potassium sulfite. So that's an ionic compound. Potassium has a +1 charge because it's in group 1. Sulfite is SO3 2- because we memorize it. It's 1 less oxygen than sulfate. And to put those together, I need 2 potassiums for 1 sulfite ion, and that's also aqueous. Now I'm going to swap partners and predict products. So I'm going to put potassium with bromide, and I'm going to put hydrogen with sulfite. So K plus with Br minus. I look at the charges and say, well, I just need 1 of each, so that's going to be K, Br. I think about this list of solubility rules, and potassium compounds are always soluble, so this is aqueous. And then my other product is hydrogen ion and sulfite ion. And the charges tell me to put 2 hydrogens with 1 sulfite. And then I should recognize, oh, that's the one that makes the gas. That's going to fall apart. And of course, I don't have room here. But what's going to happen is this guy is going to come apart into water, right? water. And what's left of that molecule after I take H2O out, which is going to be SO2. And that's my gas. Yes?
So would you show that like with another arrow?
Yeah, so that's a good question. How should you show that? Here they want the final molecular equation. And so what I'm doing here with the scribbles is showing you the process, but it's not really necessary to write this. If you were doing this and hopefully had a little more space, I should have started over further. You could write H2SO3 and then realize, oh, wait a minute, that falls apart. You could erase it and write H2O and SO2.
Okay, so you don't even need to write that, like intermediate, not actual.
You don't have to write this intermediate, no.
But if we put it down and then like...
I'd be looking at the bottom line, the final equation. Yep. Okay, so that's going to happen, but before we do that, let's make sure what we've got is balanced. Is it? No. What's something that's not balanced? Potassium. So K2 and only one K. So I need to put a 2 in front of KBr. So that took care of the potassiums, but now I need to check the bromines. Now I've got 2 bromines and over here I only have 1. So I need to put a 2 over here. And so that's fixed the bromines, and now I'm going to check the hydrogens. I have 2 hydrogens here and 2 hydrogens there. 1 SO3 and 1 SO3. When this comes apart into H2O and SO2, one of these gives 1 water molecule and 1 SO2, so I don't have to worry about balancing it. So now, as my final answer, I'm going to copy down the final answer. So HBr aqueous plus potassium sulfite is going to form 2 KBr aqueous plus, now instead of H2SO4, I'm going to write what it falls apart into. H2O liquid and SO2 gas. And the order that you put those in is not significant, as long as they're on the correct side of the arrow. Any questions?
Is there an easy way to identify what compounds are and aren't stable? I mean, even beyond gas evolution reactions?
No. So the question is there an easy way to identify which compounds are unstable, even past the gas evolution? No. Sadly, no. Yes? I would suggest balancing the equation before you break down the unstable molecule. Certainly before you throw these things in here, because you have fewer things to look at. Yes?
So, in the event that there's only a cation as one of the reactants, instead of just like an actual compound of 2 elements, how would you distribute the cation, or how do you reorganize them?
So I think what you're asking is, what if we had like a net ionic equation, or we weren't showing all of the ions? Like we had hydrogen ion here, and we weren't showing the bromide. So it could end up looking like that.
Alright, so would it change anything?
It wouldn't really change anything. Here, hydrogens, the hydrobromic acid is a strong acid, and so when it dissolves in water, it forms ions. And over here, the potassium bromide that formed is an aqueous compound, and so it forms ions. And so does anything actually happen to the bromide ion?
I guess what I'm actually asking is like if the bromide wasn't there, so I'm saying like if it was just like 2 hydrogen ions, how would you distribute the hydrogen ions to K2SO3?
Well, you can't have just 2 hydrogen ions.
Because they would be bonded, right?
Well, no, I mean, if you had a solution, you could have hydrogen ions, but there has to be an anion. Because otherwise the whole solution would be charged, and that would be like crazy unstable. So if you have a solution with hydrogen ions, there's going to be an anion in there. Now, it's possible that the question doesn't tell you what the anion is, and it's very likely that the identity of it doesn't matter at all, but there is an anion in there. And so with these gas evolution reactions, we will not be running into net ionic equations with these. There was a problem in one of the worksheets where it talked about a diprotic acid, and it didn't tell you what the acid was. So if I was told that this was a monoprotic acid, well, there's some anion, I could call it X. There's no element X in the periodic table. There's xenon, but that's Ze, Xe. And then I could have X over here. And I would recognize that, well, whatever X is, it must have a -1 charge. And so I can predict what's going on that way, even though I don't know which element it is. But I'm still going to have the hydrogens, and we're going to always do complete switching of partners. We're not going to say, well, one of the hydrogens is going to stay with this one, and one is going to go over here, and one of these, we're not going to do anything like that. They're either going to all switch or none of them switch, if that helps. Anybody else?